Welcome to the screencast on projectiles. This is an intro and it also talks about horizontal launches. So first, before we go any further, we have to define a projectile. A projectile is going to be any object which is projected by some means and continues to move due to its own inertia. And inertia of an object has to do with how much mass it has, and we'll talk about that more later. Projectiles are objects that move in two dimensions. So up till now we've talked about objects moving in the horizontal direction down the street or through the air. And now we're talking about objects that are not only moving horizontally but are also moving vertically. So like we've seen in the picture here, the trajectory of a projectile is a parabola, and it always is a parabola. It's always parabolic in nature. And for every point along the path of that projectile, we have two components to the velocity. We have a horizontal component and a vertical component. And you notice that the horizontal vectors here and the vertical vectors are not the same. And that's because the horizontal motion stays constant. It's constant velocity in a constant direction, while the vertical velocity is influenced by gravity, and so it's changing throughout that path. It's decreasing as we go up, is zero at this highest point, and then increasing as it comes down. So the most important piece of information that you can know about projectile motion is that the horizontal and vertical components are independent of each other. We watched the video in class of Mythbusters dropping a bullet and firing a bullet, and we saw that they fell at the same time, and that's fell at the same rate. They hit the ground at the same time, and so that's a good indication of what's happening and how these components of velocity are independent, because it didn't matter that the fired bullet had a large horizontal velocity motion, and the vertical direction is governed only by gravity, and so they fall at the same rate. So to reiterate, horizontal velocity component is going to be constant all the time, meaning it never changes. Equal displacements are going to be covered in equal time periods, and this is important. Initial horizontal velocity equals the final horizontal velocity, so it's constant. Why is it constant? Because there's no force acting in this direction. The only force that acts on a projectile once it's in the air is gravity, and gravity does not work horizontally. It's not going to influence that horizontal velocity. The vertical velocity component does change, and it changes due to gravity. So that means that it's not going to cover equal displacements in equal time periods. So we're going to rely on the kinematic equations to analyze this motion. Those ones for constant acceleration. And it's not just the magnitude that changes, it's also the direction. So that means that magnitude is saying that these values are getting smaller and then they get bigger. So that's the magnitude changing. And then the direction also changes. Projectiles moving up at first, and then it begins to fall down. Keep in mind here that the acceleration is constant, and the acceleration is equal to negative 9.8 meters per second squared in the vertical direction, whether it's going up or down. Now this is just a summary here. We did mention that the projectile has a parabolic path, that at all points along that path it's got velocity, and that velocity can be broken down into two components. The horizontal component is constant in magnitude and constant in direction, and that's why we see all of these arrows here being the same length and the same direction. While the vertical velocity is going to change its magnitude and change its direction. It's going to decrease as it goes up and then increase as it comes down. And one nice thing to note about this trajectory is that because it's a parabola, it's symmetrical, and so this side is identical to this side, and that'll come in handy later. Now, for horizontally launched projectiles, we know a little bit more information. We know that if it's launched horizontally, it's given just a horizontal velocity. That tells us that the initial velocity in the y direction is 0. And then again, as we mentioned, horizontal velocity is constant, so your initial x velocity equals your final x velocity. And so in class, we'll usually just write it as vx. We won't bother to put the little o there for initial because it's constant throughout the entire motion. Also, there's no upward part of the trajectory, so we're just looking at horizontal launch, and then it's going to be making its way down to the ground while moving horizontally. For horizontal launch projectiles, there are two main equations that we focus on. The first one is this x equals vx times t. So remember that the velocity in the horizontal direction is constant, meaning acceleration is 0. So that's basically this whole equation, but we've plugged in a 0 here for acceleration. If we plug in a 0 here for acceleration, that term goes away. Sorry, the import threw off that plus sign. And you're left with just this part of the equation. Now on the other side of that, for the vertical motion, the initial velocity is 0, and we're talking about the vertical displacement in that case, and so that's where this equation comes from. So this is really just a shortcut that you can use specifically for horizontally launched projectiles, because horizontally launched projectiles' initial velocity is always going to be 0. And but you don't have to memorize this shortcut. You can just look at this equation that we've been using and if you have a good understanding of how to use this equation, then you'll still be setting up the same formula here. So for example, this formula here is saying that you start off with initial position of 0, initial velocity of 0, and that your acceleration is equal to gravity, acceleration due to gravity, which is 9.8 meters per second squared, and which can also be represented by the letter g. So basically, as you see, these are the same equations. It's just this one has been simplified a bit to y equals 1/2 gt squared, and it's specific to this situation. So you can use that shortcut just for horizontal launches. So here's an example of a horizontal launch problem. There's lots of ways you can organize your information here, and this is one way you can do it. So you have one column here that says what do I know and what do I want to know. I'm a fan of making a list that has separate X and Y columns because we know that those components are separate, and so I like to keep track of what I can use together and what has to stay separate. So like we've done in class, in the X column we would have our X displacement or our horizontal displacement and our horizontal velocity here, and then in the Y column we would have our vertical displacement, our acceleration, our initial velocity, and our final velocity in the y direction. And then down at the bottom we would have time, since time can be used in either column. But let's go ahead and look at this problem. It says a plane traveling with a horizontal velocity of 100 meters per second is 500 meters above the ground. At some point, the pilot decides to drop some supplies to a designated target below. How long is the drop in the air? And how far away from the point where it was launched will it land? So a lot of times with projectiles, it can be useful to draw yourself a little picture. So this is my airplane. It's not a very good airplane, don't judge me. So we've got 500 meters worth of altitude here, and the package is going to be released from the plane and follow this horizontal projectile path. And it's going to come out with a horizontal velocity that's equal to the velocity of the plane, which is 100 meters per second, because until it's dropped, it's going 100 meters per second with the plane. And so when it's dropped, it's going to continue to go that 100 meters per second. So when we know that information, that's filled in on the table over here. So this, the subscripts got messed up on the import of this PowerPoint to my video program. We have Vx, and we have y, and we have Vy, and we have negative 9.8 meters per second squared for g. Okay, so we know that in the vertical direction there is no initial velocity. We know acceleration due to gravity is negative 9.8 meters per second squared. And we do need to say that this final position is negative, because we want to always include our negative 9.8 in our formula. And so in order for our problem to work out right, we need to think about this in terms of direction. The package is going to be falling 500 meters down, so we should have negative displacement since down is the negative direction, and we should plug that into our formula here. Sorry, again, we've got a little problem here with our import. So we have negative 500 equals 1/2 times negative 9.8 times t squared, so we're plugging into that vertical equation. It's the shortened version of the equation because we know that the initial position is 0 and the initial velocity in the y direction is 0, and so that is appropriate. We can do that. When we solve for t squared, we get 102.04. We do that by multiplying our 1/2 times 9.8. We get negative 4.9, and then we would be dividing both sides by negative 4.9. So if you do 500 divided by negative 4.9, that's where you get the 102.04, and that's t squared. And then your last step here would be to take the square root of both sides, and so you get t is 10.1 seconds. Now you can add that to the list of information that you know. And in the horizontal direction, if I want to know how far away it's going to land from the original launch point, I would be looking for the horizontal displacement. And so I would just plug into my equation my horizontal velocity and my time, like we have here. And by multiplying those, I get 1,010 meters. And that's it. That's horizontally launched projectiles. Next video will cover vertical or angled launches. Have a great day.